Today we're going to take a look at the river crossing type of problem. It's a pretty standard physics type of problem where you have a boat. It's pointed directly across a river, so here's the V boat, that's the speed or velocity of the boat, and it's pointed directly across, perpendicular to the V current, which is downstream, and we want to know at what speed and angle relative to straight across does it look like it's traveling to observer on the shore. So in a general sense, if you point your boat straight across, but it's being dragged down the river this way, it should look like it's moving diagonally in this direction. And to some observer standing on the shore, how fast would it look like it was moving? And this is actually pretty standard. So in this particular problem, we have the velocity of the boat, which is, again, straight across. And we're going to add the vectors together. So we have the velocity of the boat, which is straight across in this case. And we're going to add the vectors tip to tail. So we're going to put the tail of the river velocity at the tip of the boat velocity, and when you add them together, you get what's called the resultant velocity. This is what it looks like relative to an observer on the shore. So to add these vectors together, you take the tail of one and put it at the tip of the other, and then draw from the open tail to the open tip. In this particular problem, it says that the speed of the boat is 24 meters per second, and that the speed of the current is 7 meters per second. And so how do we find out the speed and angle that it really looks like? So this is pretty standard right triangle trigonometry and Pythagorean theorem. So I would say that we're going to call this the resultant. VR is V resultant. So if I want to find this, I would say that the V resultant squared is equal to the V boat squared plus the V current squared. V resultant squared is equal to 24 squared plus 7 squared. In this case, a little bit of math magic, and you realize that the resultant velocity is equal to 25 meters per second. And this is a classic 7, 24, 25 right triangle. If you want to solve for the angle, you can use, now that we have all three sides, you could use any of our trigonometric functions. We'll use tangent. So I'm going to say that the tangent of the angle is equal to the ratio of the opposite side to the adjacent side. Tangent of my angle is equal to the ratio of the opposite side, in this case is 7. The adjacent side is 24. If I want to solve, I'm going to take the inverse tangent of both sides. And the angle is 16.3 degrees. And that's 16.3 degrees relative to straight across. That's the first part of the problem. It's pretty standard. And again, even though the boat is pointed straight across, it is actually going and looks like it's going diagonally. Second question says, how far downstream will you land on the far shore? That is a great question. So in this problem, we have to know a couple things. One, you're going at a constant speed in the across the river direction, and we're going to need to know the across the river speed. So if I think about the across direction, in the across direction, I know the speed is constant, so I can take the displacement in the across direction, and I can set it equal to the speed in the across direction times the time in the across direction. According to the problem, the boat is 1,104 meters wide. The speed in the across direction is 24 meters per second, and I can use that to solve for the time. Now the thing about that is that regardless of how fast the current is, the boat in the across the river direction still has 24 meters per second. So whether the current was on, off, or twice as much as it was or anything, it would still take the same amount of time to get across. So in this case, the time is equal to 46 seconds. If you want to know how far downstream it landed, not a problem, because I know in the down the river direction, the speed is constant again, so I can take the displacement, the down the river distance, is equal to the down the river speed times the time. In this case, the down the river speed is the speed of the current, that's 7 meters per second, times the time we just solved for was the same 46 seconds. And it turns out that the distance in the down direction is 322 meters. So he'll land across the river, but down, instead of straight across, he's going to land down here, 322 meters. But the real question is not how far down he's going to land, because no one really wants to do that. If you're going to put your boat in the water here, you're going to want to figure out what it's going to take to just get across the river straight. So that's a new and different type of problem. So let's reset the problem. So in this new problem, what we're going to have to do is we're going to have to realize that if the current is to the right, in order for the boat to get across, I'm actually going to have to somehow angle my boat in this direction. I'm going to have to angle my boat somehow in this direction in order for the current to drag me down this way. So this time, this is the V boat. So at what angle relative to straight across would one have to point your boat so that you could land directly across? In the last problem, the boat was one of the legs and the current velocity was also one of the legs. In this case though, however, what we're going to notice is that the boat this time is the diagonal. The current is still horizontal in this case, and the resultant is this way. So here is the resultant velocity. This is the current, and this one is the boat. And when you look at this problem, this time the boat's velocity is actually the hypotenuse of my triangle, where the resultant is actually a leg. So the way we set this problem up is going to be a little bit different. So what we notice is that this time the velocity of the boat squared is equal to the velocity of the current squared plus the velocity of the river squared. And that's a little bit more interesting problem. If I want to solve for this now, I know the boat still has the same velocity, so this is still 24 meters per second squared. This is still 7 squared. And then now this is the resultant squared. And if you work this out, it turns out the velocity resultant this time is 23 meters per second. If you want to find out what angle relative to straight across, again, we're going to use our trigonometry. But this time, because we're given the opposite and the hypotenuse, we're going to use the sine. So the sine of my angle is equal to the ratio of the opposite side to the hypotenuse. The sine of the angle is equal to 7 divided by the hypotenuse, which is 24. Take the inverse sine of both sides. And we end up with my angle is equal to 17 degrees. So in order to do this, you would have to point your boat 17 degrees upstream, and it would land you straight across. It's weird though, because this time your boat would be pointed this way and you'd be moving straight across the river. Still a weird sight. Still a weird sight. How much time would it take you to get straight across? That's a great question. Well, again, if I'm moving straight across, the distance in the straight across direction is equal to the speed times the time. The same distance in the straight across direction is 1104 meters. This time it's equal to the straight across speed. The straight across speed we looked at a moment ago is 23 meters per second. Here's the time, and this time the time is equal to 48 seconds. And what you'll notice is that compared to the last one, it took you 46 seconds to get across even though you landed downstream. This time it takes you 48 seconds to get across because your speed in the across direction is actually less. Now it's 23 meters per second as opposed to 24 meters per second the first time.